Okay, this video we're going to talk about section 7.2 and also section 7.3. 7.3 is just applications of 7.2, so just word problems. All right, 7.2, linear programming, the graphical method. This section introduces two ways to get the answer. However, we're really going to focus on one way. And let me try that English again. We are only going to focus on one way. Close enough. To begin, we first talk about how to turn English into math. So you'll do more of this in the next section. But if you need to, pause the video, read the words. They're on the screen. Okay. So the question at the end there is, how many of each should be sold? Yep. To maximize revenue. Do we know how many chairs and nightstands need to be sold? No. So that's where our variables come from. Well, X will be the number of chairs, and Y would be the number of nightstands. Okay. Don't be lazy. Do not say X is chairs and Y is nightstands, because X plus Y would be like, a little table for a child. And there's a little table. Oh, it looks like a pie. And then there's a little chair for the nightstand that goes. And little kids right here. Kids are mainly just large heads, right? Oh my God, he looks so upset. All right. There you go. I don't know how to make him happier. Oh, I made him. Oh my God, he's evil. He's pure evil at this point. Anyways, don't be lazy with naming your variables. Okay. So in a linear programming problem, you are going to maximize or minimize something. Here, we are maximizing revenue. So we'll say maximize. And you pick a variable. You can pick R for revenue like we did in chapter 3. 3? I want to know with a yes. Or instead, what we'll do is we use a generic variable, Z. And again, we're maximizing revenue. So ask yourself, or read the problem, how much money comes in for every chair you sell? And you'll notice it says you make $70 per chair. Sells for $70. And how much money comes in for every nightstand you sell? $120. Okay. Now we're going to try to maximize this subject to, and we're going to try to maximize it subject to restrictions. If we had a magical forest of wood and then also endless hours of labor, then we would just pop out nightstands, because why even bother with chairs? Because nightstands make you more money. But an infinite amount of wood and an infinite amount of labor does not exist. So this is where your restrictions will come from. You'll have a restriction on how much wood you have available and how much labor hours you have available. These restrictions turn into inequalities. So a chair needs 5 pieces of wood and you have X chairs, so that's 5X pieces of wood just for the chairs. And a nightstand needs 11 pieces of wood, and you have Y nightstands, so plus 11Y. And then it says, suppose on a certain day you have at most 80 pieces of wood. At most is an inequality, less than or equal to. In this case, 80. So 5, 11, 80 all deal with wood. So put all those numbers together. Take a second, pause the video if you need to, and I want you to write the constraint, or the inequality related to labor. Hopefully you came up with 9x, 9 hours of labor per chair, and we have X chairs, plus 13y, we have 13 hours of labor per nightstand, and we have Y nightstands, and we have at most 240 labor hours available. Okay. The last thing to note is that you can't have a negative amount of chairs and you can't have a negative amount of nightstands. So X and Y are both greater than or equal to 0. So this whole thing is the math equivalent of all this English that we have up here, and this whole thing is called a linear programming problem. And again, the purpose of a linear programming problem is to maximize or minimize something under restrictions, under constraints. Before we dive into the next slide here, let's define some terms here. This thing that you're maximizing is called the objective function. And again, it could be a maximize or a minimize. So like for instance, if Z represented the cost, you'd probably want to minimize cost. You wouldn't want to maximize cost. Subject to, the inequalities combined are called constraints. The first two inequalities are called functional constraints because they come from the problem themselves. So those will vary from problem to problem. And then the last two inequalities are called non-negative constraints. These guys don't vary. You pretty much see them in every single application from here on out. Notice I said application. For a generic problem that's not coming from a word problem, you might not see those guys. And as you learned in the 7.1 example videos, that if you see that paired together, when you're graphing it, you're only focusing on the first quadrant. Because that makes sense, because X and Y means something. You can't have a negative amount of something. So that's why those two are there. Okay, so this slide was just to go from English to the to the math. And now let's formally define a linear programming problem. A linear programming problem in two variables, x and y, consists of maximizing or minimizing the objective function. Blah, blah, blah. You can read. So that is our goal in this section, is to find the variables x and y so that the objective function, z equals whatever, is maximized or minimized depending upon the problem itself. Now, in 7.1, corner points were stressed, and finding corner points were very, very important. So make sure you know how to do that, the intersection of two lines. I'm pretty sure in the videos I show you how to use your calculator. As he looks real quick without actually knowing.
Now what we're going to do is switch to systems.
Oh,
systems
no.
just means you have more than one.
No.
0, 0.
Alright, so I have to talk about finding those corner points with you. Stop talking. Alright, let's do that now. Before we continue. Click. Can I make that maximized without... Can I click on this? That's going to open that. I don't want to hear myself, though. No, stop talking. Okay. So, I'm going to show you how to use the calculator to find corner points quickly. Well, quicker, I should say. So, remember, a corner point is the intersection of the two boundary lines that touch the feasible region. So in part C here, this point right here, the intersection of the blue line and the green line, would be a corner point because it's where they intersect and it's where, and it touches the feasible region. This point up here is not a corner point because it doesn't touch the feasible region. It just happens to be a point. So to find out where these two lines intersect, you would have to bring both variables to the other side. So as a comment, please note that x equals 4y is the same thing as x minus 4y equals 0. Okay, so what we're going to do is we're going to create a matrix. So second matrix, scroll over to edit. I'm going to make a new one. I'll just call it B. And we'll make it 2 by 3. 2 rows, 3 columns. Since our first equation is 1, 1, 5, we'll type in 1, 1, 5. In our second equation, if we brought all the variables over, it would be 1x minus 4y equals 0. So 1, I typed in a 0 there. 1, negative 4, 0. Okay. We might not get a pretty number here, but it's not the point. Okay. So first step is to write into your calculator as a matrix the two lines that you're looking for to intersect. That's why labeling the graph is so important. So I'll talk about this one in a second. So once you have your matrix set up, we'll go to second quit to get out of there. We'll go back to second matrix. We'll scroll over once to math. And it's easier if you scroll up and you're looking for RREF, reduced row echelon form. Select RREF. Then go back to second matrix and then select the matrix you created. I created D. And it's always good to close out your parentheses there. And then hit enter. Based on what we did in chapter 6, we know that this says x is 4, y is 1. So the point 4, 1. Do not ever look at the graph and go, here's where the point must be. Because if your graph is wrong, you're not going to get the right coordinates. And it's possible that your coordinates are fractional or decimal. So you would definitely not get the correct answer. Please rely on the RREF command in the calculator. The only time you really don't need to do it is, for instance, like in our graph to the right here. This point here would have been found by finding the y-intercept for the green line. So you probably would have already known that that's 20/7. And this line here, its x-intercept is a corner point that would have been at 3. So, and also the origin happens to also be 1. So these guys out here, the ones that touch the axis itself, you probably don't need the RREF. But the points that are floating in space, like this guy out here, please do an RREF. Okay, so that's how you find corner points using your calculator. You go over here now. This is your home. So the reason that corner points are so important is because, here we go. Oh, here's where I define a corner point. Is because all you really have to look at is the corner points. So the point that maximizes or minimizes an objective function happens to be the corner points. Great. And that's all the purpley box. It's sort of pinkish. A mauve, if you will. I think that's the color. If you're saying out loud, that is, I can't hear you. If you said it, that is out loud, let me know. Thank you. That's all that box is saying is, hey, just look at the corner points. So there is a method designed to just look at the corner points, and it happens to be the corner point method. Boop. Hey, look, the corner point method. Step 1, find all of the corner points of the field region. Okay. Step 2, evaluate the objective function at each of the corner points. Okay. Step 3, select the optimal solution based on if the objective function is maximized or minimized. All right. Just like plotting inequalities, this might not make any sense until you do an example. Pause the video if you need to. I am going to copy down the example from video number 82. And I'm just going to make up something. I'm going to add to it. I'm going to say maximize z equals 2x plus 3y. Making that up. Okay. So step 1, you would find all the corner points. Well, in that video, we already found the graph, so I'm just going to go one step further and find the corner points. I think that's sufficient. We'll find out. Oh, I might need more. I'll do a couple more. Can I draw lines with this? Does anyone know? I can't hear you. So 5x plus 3y equals 15 would have an x-intercept at... Oh, I hate when it does that. X-intercept at 3 and a y-intercept at 5. 1, 2, 3, 4, 5. All right. Feel free to judge. It's hard to do. It's okay. I did a good job. So 5x plus 3y equals 15. Great. And I would be shading below. If you don't know where I'm getting this from, please rewatch video 82. And then the next one, 2x plus 7y equals 10. The x-intercept would be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Y-intercept would be 27ths. So just under 3. I am not going to hit that point. I'll just make that much bigger than what it should be. Okay, 2x plus 7y equals 20. Same deal, shade below. Again, no wimpy shading. All right, so our feasible region is bounded and happens to be this one here. Hooray, stay in the lines. Okay. So by design, we know some of our corner points already. For instance, this is 0, 0. And this one is 0.27. And this one is 3, 0. But notice we have one floating in space out here. So the ones that are floating in space, that's where you pull out your calculator. And we will make a matrix. So second matrix, go to edit. Oops. I'm going to just overwrite A. It's another 2 by 3. That point that we need is going to be the intersection of two lines. It's the intersection of 5x plus 3y equals 15 and 2x plus 7y equals 20. So we'll make a row in our matrix, 5, 3, 15, and the other one will be 2, 7, 20. Just double check your numbers. Looks good. We'll quit out of here. We'll go to second matrix, scroll over to math, scroll up, and you're again looking for RREF. Select RREF, and then one more time, go back to second matrix, and under names, pick the matrix you created. Hit enter. Now here, gave us crazy decimals. It's going to be okay. You can, if possible, usually it is, you can go to math and pick the first one, convert to fraction. Okay. Is it the prettiest answer? No. Is it the correct answer? Yes. Okay. So guess what? All of that is step 1. We didn't do anything new yet. That was all step 1. That was 7.1.7. That was section 7.1. Okay. Step 2. Evaluate. What does evaluate mean? It means plug it in. So I'm going to list the corner points and only the corner points. The order in which you list them does not matter. Oh, forgot my 2. And evaluate is, I'm going to put in 0 in for x, 27ths in for y into our inequality, into our objective function for the first point in similar manner for the rest ones. So if I put in 0 in for x, 27ths in for y, I get 0 plus 67ths, which is just 67ths. Oh, I almost made a 7 over there. If I put in 0, 0, I get 0. If I put in 3, 0, 2 times 3 plus 3 times 0 is 6. And then if I plug in that monster, oh my gosh. put it over here. Let's see. 2 times 45 29s plus 3 times 70 29s. This is probably going to be an ugly fraction, so I'm just going to say convert to fraction. 329s. Okay, so funsies, let's figure out what 67ths is as a decimal, and then 329s. It's pretty close. Okay, we are trying to maximize. So we're in step 3 now. We are trying to maximize. Notice 329ths was the biggest number out of this entire list. Because this was 8 point something, this is 0, this is 6, this is 10 point something. So out of that list, this guy was the biggest, 329ths. So 329ths is called the optimal value. Optimal value. I'm going to take a nap. And then that point, which I don't want to say the coordinates anymore, is called the optimal solution. Hooray! So that's the corner point. Step 1, find all the corner points. Please use your RREF command in your calculator. It'll save you a lot of tears. Step 2, plug in those corner points into your objective function. Step 3, pick the biggest if you're trying to maximize. Pick the smallest if you're trying to minimize. That's really about it. If this question was, what's the minimum? You would have said 0, 0 at 0. It gives you 0. That's it. Now, as a comment, watch out, because sometimes, let's suppose that you had an unbounded region, like this guy here. If you have an unbounded region that's unbounded in the positive direction, meaning it's always going to grow and grow and grow as x and y both get bigger, then for these types of regions, you do not have a maximum, but you do have a minimum. So let's compare. The darker purple one down here, it's a little blue also, is bounded, remember, enclosed on all sides. A bounded region will have a maximum and a minimum. An unbounded in the positive direction will have a minimum but no maximum. So that's a huge difference between the two. So watch out for, there might be some trick questions to where you won't get an answer because there can't be an answer. And that may see, let me go back here. That's sort of what this says here. It's actually what this says. If the region is unbounded in the positive direction, the objective function has a minimum but no maximum. So there is that. If it's bounded, you have both a maximum and a minimum. Okay. So that should allow you to watch a bunch of videos, 83 through 88. 83 through 88. So watch all of those. 83 through 85 would be 7.3. I'm sorry, 7.2. And then 86 through 88 would be 7.3. I would take it in stages. Do the 7.2 stuff. Make sure you're comfortable with that. And then do the 7.3 stuff. Because, again, 7.3, it would basically be doing this problem, converting it from English to math, then solving the math like this, and then convert it back to English. So it's got an extra part of the end, a beginning and an extra part of the end. Okay, that's it. Have a good day.